Hello, Enriched Algebra 2 students. I can't believe I forgot to record this video this weekend, so here it is. All right, let's see what we got going. Find the x-intercepts and the vertical asymptotes. Okay, so the x-intercepts, those we find based on the last worksheet from setting the numerator equal to 0 and solving. This one we can solve by factoring. We can pull out an x, and we're left with x minus 3 equals 0. So there are two x-intercepts, 0 and 3. The y-intercepts we won't worry about. I did that intentionally. And the vertical asymptotes, that you find by setting the denominator equal to 0 and solving. X squared plus x minus 12 equals 0. This one we can solve by factoring. X times x is x squared plus 4 minus 3 gives you the 12 and the 1x. So there are two vertical asymptotes at -4 and at 3. Okay, now we will double check everything, see if everything works out fine by graphing it on a graphing device like Desmos and then just copying it onto my paper. So just moments ago, I graphed it on a graphing calculator, and here is what the graphing calculator has. It has an imaginary vertical line at -4, and there's one part of the graph that goes like this, and one part of the graph that has a y-intercept and an x-intercept of 0, and it goes like this. Okay. So, according to the problem, we have two x-intercepts and two vertical asymptotes. Okay, now look over here. Holy cow, there's only one vertical asymptote at x equals -4. Oh, and look, two x-intercepts, there's only one x-intercept of 0. There's only one x-intercept of 0. So we have lost the second x-intercept of 3 and the vertical asymptote at 3. And strangely, these are the same number. Coincidence? I think not. Okay, because they're the same, they kind of cancel each other. Okay, where did they go? Okay. So what do we notice? We lost the x-intercept of 3. We lost the x-intercept of 3 and the vertical asymptote of 3. Where did they go? They are gone. Okay, now, if you plug in stuff into Desmos at things like 3, or things close to 3, so 2.9, 2.99, 2.999, and 3. So right at 3, the question is now, what is going on? Are there outputs as you get closer and closer to 3? Are there outputs? And the answer is yes. But if you put into Desmos into a table at 3, it'll tell you the output is undefined. But yet there's no asymptote. So if there's no asymptote, but it's undefined, there's no output. So in my graph, I have an output at 3. I have the output as like, whoops, I didn't mean to do that. I have my output at like, I don't know, a half or something like that. But yet, on the table in Desmos, it says at 3, the output is undefined. So I can't have an output at 3, but yet there's no asymptote. So I will put in a small open circle denoting that there is a hole in the graph. But it's so small you can't see it. It's infinitely small because really, really close to 3, there is an output. The only thing that doesn't have an output is at 3. So this hole is actually infinitely small. But it is infinitely small. You can't see it. Okay. So that's where the vertical asymptote and x-intercept went. They got sucked into the black hole. But it's really small, so you can't see it. All right, hopefully that made perfect sense. What occurs at 3 is a hole, which you should mark with a small open circle on the graph. I already did. Okay. How can we find this in a graph? Well, I have no idea. Wait a second. Let me think about this. The x-intercept and the vertical asymptote were both 3, and that's where there was a hole. So I wonder what would happen. So if I have x squared minus 3x, this is the original problem, over x squared plus x minus 12. X squared plus x minus 12. They're at the same place. What if I factor the top and factor the bottom, which, by the way, I've already done, and the x minus 3's cancel? So it would appear that if something cancels, there's a hole. If something cancels, there is a hole in the graph. An infinitely small hole, which if you graph on a graphing calculator, you can't see because it's so small. Okay. Well, that was interesting. Now, someone had asked about horizontal asymptotes, and I said it's not mathematically hard, but there's a strange formula. Here is the strange formula. It's this whole shebang is the strange formula. Okay. What it says. Okay. What it says is that this n and m, see these n's and m's? These n's and m's are the exponents. Ax to the n, the n is the top exponent. N is the largest top exponent. N is the largest exponent on top. And m, you can't see the m anymore, but that was an m. M is the largest exponent on the bottom. And m is the largest exponent on the bottom. Okay, and then you look at the exponents. If they're the same, the horizontal asymptote is a over b. A over b, the a and the b are the numbers in front of the largest exponents. The a is the number on top. The a and the b are the numbers in front of the largest exponents. Okay. If the top exponent is smaller than the bottom, then the horizontal asymptote is y equals 0. If the top exponent is bigger than the bottom exponent, there are no horizontal asymptotes. And I have looked into why all of this is true, and the explanation is very complicated, and trust me, you don't want to know. It just works. Okay, so let's try it out. Find the holes, x-intercepts, and asymptotes. You factor first in case there's a hole. The first thing you do is factor. First factor. So we can factor the top into 2x plus 3 and 2x minus 3. The bottom, that looks hard to factor. We can factor into 2x times x is 2x squared, and 4 times 3 is 12, and we want a plus 4 and a minus 3. Okay, now it's correctly factored. Now I can cancel the 2x plus 3's. So the second thing you do is check for holes. There's holes if something cancels. There's a hole at whatever cancels, whatever makes that 0. Add 3 to both sides, you get 2x equals 3. Divide by 2, you get x equals 3 halves, or 1 and 1 half. So the second thing you do is look for holes. If something cancels, there's a hole. Okay? If something cancels, there is a hole. If something cancels, there is a hole. All right. Now, you use your new equation. Use your new equation, which is 2x plus 3 over x plus 4. Now you look for your intercepts and asymptotes. Okay. Now, you must use your new equation, not your old equation. Okay, so the x-intercepts come from setting the new numerator equal to 0 and solving. Subtract 3 and divide by 2. You get negative 3 halves, or negative 1 and 1 half. The y-intercept comes from putting 0 in for all your x's in simplifying. So you get 0 plus 3 over 0 plus 4, which is 3/4. Your vertical asymptote comes from setting the denominator equal to 0. And the horizontal asymptote is the strange formula. Okay, in the new equation, the exponent on the bottom, the largest one is a 1, and the largest one on the top is a 1. Our exponents that we're comparing are 1 and 1. 1 is equal to 1. The exponent on top is the n. n is equal to m. So you look at your cases. N is equal to m is the top case. If n is equal to m, then the asymptote is a over b. So the asymptote is a over b. A is the number in front of the x with the largest exponent, and b is the number in front on the bottom. So 2 over 1, which is 2. We've done it. We've found all of the information, the interesting information about the graph. Okay, let's look at the practice problems. Find the holes, intercepts, and asymptotes, show work, and then do some matching. Yeah, you should be able to tackle this. You might have some questions, but I will happily answer them soon, later.